So we got Z12 here. As we know, that's as a set, it's got 12 elements, 0 through 11. As a group, it's only a group under addition, mod 12. The goals were to find the orders of every element, find the generators, and find all the subgroups. So I just went ahead and started one by one. Of course, the number 1 has order, whoops, that's a mistake actually. Order 12. It's a generator. Hopefully, when I was working on this, you didn't get too messed up by that, if you happen to look at what I did. That is a generator of the whole group. 12 times 1 is 1 added to itself 12 times does give you 0, and it's the first positive multiple of 1 that gives you 0. That's important as well. I emphasize the first issue on these two examples here and here, but then I don't bother emphasizing it again, though it's still important, obviously. 2 has order 6 because, well, first of all, 6 times 2 is 0. 2 added to itself 6 times is 0. And because nothing smaller than 6 works. 1 times 2, 2 times 2, 3 times 2. None of those give you up to 12 to get you back to 0 mod 12. So the order of 2 is 6. The order of 3 is 4. 4 times 3, 3 added to itself 4 times is 0, but also nothing, no smaller multiple of 3 gives you 0. Therefore, the order of 3 is 4. Not bothering to say those things for these other examples. The order of 4 is 3. The order of 5 is 12. 5 is a generator. The order of 6 is 2. The order of 7 is 12. 7 is a generator. And if you were feeling unsure about like whether 5, 7, and 11 were generators, I mean, you could list out all the multiples. For example, if we do it with 5, let's go ahead and take the time to do so. Well, 0 times 5 is 0. I'm writing 0 first. I could have written it at the end. 1 times 5 is 5. 2 times 5 is 10. 3 times 5 is 15. Mod 12 is 3. 4 times 5 is 20. Mod 12 is 8. But also 3 plus 5 is 8 is another way to think of that. 5 times 5 is 25, mod 12. Oh, did I make a mistake then? Am I good so far? So 8 plus 5 is 13. Mod 12 is 1. Okay, I was getting confused about it being 1. I was thinking of the U groups, and 1 being the identity of the U groups, and that got me confused. 6 times 5 is 30. Mod 12 is 6. Also 1 plus 5 is 6. We can just keep adding 5 here. Now 6 plus 5 is 11. 11 plus 5 is 16. Mod 12 is 4. I mean, yeah, we already have more than 6 elements. It's got to be a generator. Nothing between 6 and 12 divides 12. 4 plus 5 is 9. 9 plus 5 is 14. Mod 12 is 2. Almost out of room on my paper. 2 plus 5 is 7. 7 plus 5 is back to 12, which is 0 mod 12. There we go. Order of 6 is 2. Order of 7 is 12. 7 is a generator. Order of 8 is 3. Order of 9 is 4. The cyclic subgroup generated by 9. 0, 9. 2 times 9 is 18. Mod 12 is 6. 3 times 9 is 27. Mod 12 is 3. 4 times 9 is 36. 36 is divisible by 12. You're back to 0. Order of 10 is 6. Order of 11 is 12. The generators are 1, 5, 7, and 11. There's 4 generators. Hey, those are the numbers less than, positive numbers less than 12 that are relatively prime to 12. Those are the elements of U12. That's not a coincidence. The generators of Z12 are the elements of U12. And that always works. The generators of Zn are the elements of Un, not an accident. And those are the positive integers less than 12, in this case, that are relatively prime to 12. The GCD of those with 12 is 1. Yeah, and if you list out all the subgroups, there they are. There are repeats. This is I didn't have to do as much as I did there because there are repeats. These three match to the original entire group. Whoops, this is a mistake. Oh no, okay, sorry. Arrow at the wrong spot. Oh, I did meant, you know what, I also should have written the order of 0 as 1. I forgot about that. Those match this one. There's more matches. This one matches this one. No, not really. Okay. This one matches this one. And this one matches this one. You can write those subgroups with either notation. You could, for example, this one you can write either as the subgroup generated by 10 or as the cyclic subgroup generated by 2. Are these all the subgroups of Z12? They are. I haven't proved that, though the proof is in the book. It's the fundamental theorem of cyclic groups. Hey, fundamental theorem, that sounds important. Every subgroup of a cyclic group is also a cyclic group. And in fact, more, you could say more. For each divisor of the entire group, Z12 has order 12. Its divisors are 1, 2, 3, 4, 6, and 12. For each one of those divisors, there's a unique subgroup that's a cyclic subgroup. There's your unique subgroup of order 1. There's your unique subgroup of order 2. There's your unique subgroup of order 3, order 4, order 6, and then the entire group. And if you did try to make a lattice diagram like you found on page 85, you put the entire group at the top. You put the trivial subgroup at the bottom. And in between, you draw line segments in such a way that when there's a line segment connecting something lower to something higher, the something lower is a subgroup of the something higher. If that makes sense. So for example, 0 is a subgroup of the cyclic subgroup generated by 6. That one there. That's a subgroup of the cyclic that's a subgroup of the cyclic subgroup generated by 3. Like that. I'm purposely putting these a little bit sideways. 0 is also a cyclic subgroup of the subgroup generated by 4, which is not a subgroup of this and not a subgroup of that. So I need to put it over here, say, maybe a little higher because it's a little bit bigger than the one generated by 6. I've also got the cyclic subgroup generated by 2, has order 6. This one's a subgroup of it, but not that one. Am I missing any? So subgroup order 1, 2, 3, 4, 6. Okay, then these are subgroups of the whole group. Not the prettiest way to make the diagram, but it works. Notice on page 85, if you've got your book and you're looking there and you're looking at the subgroups for Z30, this thing is called a subgroup lattice. It's a bit more complicated for Z30. It's like a directed graph, actually, in discrete math. You could think of this as a directed graph.
Could you draw a line connecting 2 with 6?
Yes, you can. Thanks. My answer is incomplete. Thank you.
And would you have to connect everything with 1, or is that just implied?
Just to make the diagram look prettier, more complete, then yeah, it's good to do.
Okay.
Any questions? Any other questions at all? Okay, so now let's spend our time focusing on the questions you sent me. And as I work through these questions, I'll talk about things we've talked about so far. We'll review some things and maybe do some examples. And focus, I think the most important thing to focus on, besides your homework for Friday that you got to turn in, and besides the lecture, is really understanding chapter 4 well. I mean, you should have read it before today, but if you did read it, which was good, you're probably going to want to reread it because it was a hard chapter. It's not an easy chapter. Theory about cyclic groups. It definitely feels difficult the first time you read it, though later on in the course you'll look back and say that's relatively easy compared to what we do later. So I don't know if that's a positive thing to say or not, but it will get easier. The things that seem hard at first do definitely get easier. And they get easier also when you think about examples. Maybe you don't completely understand a proof right away, or maybe you say, oh, I never could do that proof on my own. And that can be okay. If you can at least understand the theorems, what they say in terms of examples, that's definitely a positive development, okay? So don't beat yourself down too much if you don't completely understand a chapter right away. It takes time, and it takes thinking about examples. Okay, so the first question I got was a question, can I clarify a cycle notation essentially with permutations? Can I clarify how when you multiply, quote unquote, these cycles, 1, 2, 3, and times itself, I get 1, 3, 2. Okay, so we're talking about a permutation in cycle notation. That could represent a permutation in S3. It also could represent a permutation in S4 or S5 or S6 or S7 or Sn for any n greater than or equal to 3. It represents a function that maps 1 to 2, 2 to 3, and 3 back to 1. What happens when I square it? Well, first realize it's squaring in the sense of group theory, but the operation is truly function composition. So it's not squaring in the sense of multiplication in the usual way. Composing it with itself, and as always with functions, when you're composing them, you work right to left. So I think about, I mean, they're the same thing in this case, so it really doesn't matter. But if they were different, I definitely start with the one on the right and go to the left. So I first need to think about what this maps 1 to. Because of the notation, 1 would get mapped to 2. Then the output of that function, getting plugged into itself again, the notation means 2 gets mapped to 3. So ultimately, under the composition, 1 gets mapped to 3. When the question that was asked there addresses, what do you do next? And I think what the question, to answer the question, so 1 goes to 2 and 2 goes to 3, so I put 3 in the second place. Your mistake was starting with saying, oh, 2 goes to 3. You need to think about what 3 goes to next, not what 2 goes to next. because we're now at the 3. We don't want to go in order of what does 1 get mapped to first, then what does 2 get mapped to, then what does 3 get mapped to. You want to think about these things in order. 1 got mapped to 3. Now think about what 3 gets mapped to. Because that's what you're doing with cycle notation. That's why you do it that way. 3 gets mapped to 1, but then 1 gets mapped to 2. And that's why you don't go back to 1. 2 ultimately does get mapped to 1, but you need to write it in the cycle notation first. 2 gets mapped to 3, but then 3 gets mapped back to 1. So ultimately, under the composition, 2 gets mapped to 1. Does that make sense? So when you're writing the answers in cycle notation, the key is you think about the numbers in the order that they come. Because that's what the cycle notation is representing. A couple of people had questions about centers and centralizers and subgroups and intersections of subgroups, and related to what we did on the other day, as well as in lecture 7. Let's just review those definitions. First, of center and centralizer. I'll just go ahead and look at them in the book here. All right, the center of a group is different than what we talked about the other day. We were talking about centralizers of elements, C of A. They're different concepts, though they're related. Z of G, the center of a group, is the set of all elements of the group that commute with every other element of the group. Set of all A and G, so that A of X equals A times X equals X times A for all X and G. They commute with everything else. You always have at least the identity in the center. If G is abelian, what would Z of G be if G is abelian? All the elements of G, in other words, all of G. So when G is abelian, Z of G equals all of G, it's possible, conceivably, that in some cases, Z of G is just the identity element. In fact, that's true in D3, which is isomorphic to S3. It's just the identity element. It's not true actually in D4, and you'll see that in the book. Symmetries of a square has a bigger center than just the identity. In a sense, you might think of this intuitively as a measure of how, when you've got a non-abelian group, it's a measure of how non-abelian it is. The smaller the center is, the less abelian the group is. There's sort of an intuitive way to think about it. Non-rigorous, non-precise way to think about it, but that's kind of the intuition. And if the center is not the entire group and not just the identity, it's somewhere in between, then it's non-abelian, but maybe less non-abelian than something where the center is just the identity. The center is a subgroup for any group, including even if the group were infinite as well, by the way. There's nothing about the group being a finite group here. Centralizers, there's only one center for a given group. There are many centralizers. There's a centralizer C of A for each element A in G. C of A is the set of all elements of G that commute with that one element A. Think about this in extremes. C of the identity, C of E, is always the entire group, no matter what the group is, because everything commutes with the identity. For non-identity elements, C of A certainly contains all the powers of A. I mentioned that the other day. So it would contain the cyclic subgroup generated by A, for example. C of A is bigger. You can picture these things with, kind of like Venn diagram types of things. Here's E. Say here's A. C of A, the centralizer of A in G, certainly contains both E and A, and also powers of A squared, A cubed, etc. So it definitely contains the cyclic subgroup generated by A. It's possible, a priori at least, that the cyclic subgroup generated by A is a proper subgroup of the centralizer of A. Might be equal to it, but might be smaller. Depends on the situation. And C of A is a subset, a subgroup of G itself. But if you got some other element, B, okay, I'm going to draw this kind of funny. Say this is B here, and maybe B squared's over here, and B cubed's over here. The centralizer of B contains all those powers, but it also has to contain E, so we kind of got to snake it in here. You can't take this kind of picture too literally, but somewhat literally. So maybe this is the maybe this is the cyclic subgroup generated by B, and then the centralizer of B contains that. And it could contain some powers of A as well. It's possible. I guess I drew it to contain A, but that may or may not be the case. The center is the intersection of all the centralizers. You can say Z of G is the intersection of all the centralizers. And since you don't know whether there are finitely many elements or not, you have to use sort of a more general kind of intersection notation. Like that. This means intersect every centralizer with every other centralizer. In other words, the elements of Z of G are in every centralizer, is a way to think of that. Yeah, you can draw pictures like this. They're somewhat helpful, but they're certainly not the end all be all. You got to think about other issues. You got to think about other things. You got to think about examples for this to have more meaning. You might wonder why it's important. That's another question altogether. One big reason the center of a group is important is because of something called the GZ theorem. See if I remember where it is here. Maybe chapter 9 or 10, one of those two chapters here. Yeah, it's one of either chapter 9 or 10. There's something called the GZ theorem. I'm not finding it. Oh, there it is. It's on page 181. This doesn't have much meaning when you look at it at the moment. Like, what in the world is that? I see G, I see Z of G, but why am I dividing G by Z of G? That's not been defined yet. It's called a factor group, but we won't get there until after exam 1. It's a fairly useful theorem in some situations. To conclude that a group is abelian, maybe for some reason you can't conclude it any other way. Or maybe, if you think about the contrapositive of this, if G is non-abelian, then this group is actually not cyclic. Would be another application of it. And it's more important than you might imagine just looking at it at first glance. Centralizers, I think of centralizers having an application in an even more advanced topic in here. Chapter 24, which we will actually not cover, but somebody did cover it for their senior seminar paper. They're called the Silo theorems. Don't say silo, say Silo. Silo theorems. Centralizers play a role in there. Yeah, for example, you can see them in this theorem here. There's C of A there. So they're constructs that you can certainly think about as examples of subgroups. And think about particular examples and compute centralizers in the center. Just examples of subgroups at the moment. It's not clear how they're useful in studying groups. And when we talk about usefulness, we do mean usefulness in an abstract sense to study groups and their structure. That is our big goal, is we want to understand groups and the kinds of things that can happen with groups. We're trying to classify them. It's like we're zoologists and the groups are different animals we're studying. We're trying to classify groups, especially finite groups, based on their order, based on how many elements they have. That's going to be the main theme of the first month and a half to 2 months here in the class. Can I clarify anything there?
Can we do an example with the center of a group?
Sure. So the book, I think, does D3, if I recall correctly. They talk about the center of D. Okay, they do a general example. The center of Dn is just the identity when n is odd, so the center of D3 is just the identity. It's the identity and also the rotation by 180 degrees when n is even. So D4, for example, symmetries of a square would have a center that includes a rotation by 180 degrees. If n is odd, R180 is not even in the group. It's not even in Dn. Your polygon, your regular polygon has to have an even number of sides for a rotation by 180 degrees to be a symmetry. Does that make sense? So squares, hexagons, octagons, you all have symmetries where you rotate by 180 degrees. And when it's odd, like a pentagon or a triangle, you can't, R180 is not even a symmetry of it. Certainly R0 commutes with everything. They give an argument here about why R180 does as well. So yeah, they're giving a sort of a general argument here. I mean, it's going to be easier to think about when you look at a particular example, I think. I guess we could go back to chapter 1. Is that the Cayley Table of D4? I mean, if you want to just see it, the Cayley table is the best thing to look at. Certainly R180 commutes with all the other rotations. So the question is, does it commute with all the reflections, the flips? R180 composed with H is V. V composed with R180 is H. Wait a minute, looking at R180 composed with H is V. I meant to look at H composed with R180 is also V. That matches that. R180 composed with V is H, and V composed with R180 is H. Yeah, just look at this row right here and this column right here. You go in the same order. V, H, D prime, D. That shows R180 commutes with the flips. R90 and R270 don't. You go across this row here and this column here, you do not get a match. D and D prime, for example, don't match. And same kind of thing with R270. This row and this column here. So R90 and R270 are not in the center. R180 is. R0 certainly is. None of the flips are in the center. they don't commute with each other, for example. Well, H commutes with V, but it does not commute with D or D prime. H composed with D is R90, but D composed with H is R270. R90 and the R270 there and there don't match. Is that helpful enough to think about? That's probably the simplest example to think about is like D3 and D4. If we try to think about other non-abelian examples like D5 or D7 or something, D6, the Cayley table is getting so big it would be difficult to make and would be difficult to, it would be very time consuming. With the Z groups, Zn, and with the U groups, Un, those are already abelians, so their centers are going to be the whole group. We haven't really studied many non-abelian groups, just the Ds and the S's. And remember, D3 is isomorphic to S3. And because of that, that would also mean the center of S3 is just the identity. D4 is not isomorphic to S4. D3 is isomorphic to S3, but D4 is not isomorphic to S4. They don't even have the same number of elements. In fact, Dn is not isomorphic to Sn if n is greater than or equal to 4. Dn has 2n elements, n rotations and n reflections. Sn has n factorial elements. When n is 4, you've got 8 elements versus 24 elements. There's no way they can be isomorphic. Question? Explain what Sn is. Isomorphic means if you draw the Cayley table in an appropriate way, the structure is going to match up effectively. That's not the official definition of isomorphism, and we haven't gotten to that yet. That's chapter 6. I can briefly say what the official definition is a little bit. There's got to be a one-to-one and onto function from one group to the other that preserves the operation is the key. It's analogous to linear transformations in linear algebra that were one-to-one and onto. You might remember T of U plus V must be equal to T of U plus T of V in linear algebra for linear transformations. And also T of alpha times U, where alpha is a scalar, must equal alpha times T of U. Those were two properties that linear transformations had to satisfy. Those are operation preserving type properties, and these one-to-one and onto functions between two groups must satisfy something similar to that to be isomorphic. So I haven't officially defined it yet, so you don't need to worry about it yet, as far as like on homework problems. Trying to give you some intuition first. And you know, we're doing these SN examples before you've gotten to chapter 5. I think it's good to think about, you know, examples before you read the theory. No, pretty much nobody can just read theory. Right? It's just too abstract, makes you feel too tired. Without thinking about examples, at least. The examples help give life to the theory. They can make the theory more exciting, you might say. They can, if you get into it enough. Another question is about this notation that comes up in the book. I'm not going to make a big deal out of this as far as like really testing you on this concept, but we could briefly talk about it. You can talk about subgroups that are generated by more than one element. What page is it on? 636. Yeah, page 636. So there's a discussion of this here, this general notation where you put the pointy brackets around something. So the pointy brackets around an individual element is the notation for the cyclic subgroup generated by that element. As a set is the set of all powers of the element. But in general, if you got a set S that may have just one element, may have two elements, may have three, may have infinitely many elements, you define this notation to mean to represent a subgroup of G by definition. It's easiest to think of it as the smallest subgroup of G that contains S. And you'd call this the subgroup generated by S. Will it be cyclic? Maybe, maybe not. It depends. Certainly, if G is a cyclic group, then it will be cyclic, no matter how many elements you're talking about from S, by that fundamental theorem of cyclic groups, that every subgroup of a cyclic group is it's itself a cyclic group. Before we look at the examples, just visually, and you can once again draw a Venn diagram. There's G, there's S. S is not necessarily a subgroup of G. It's just a set, a subset. The subgroup generated by S contains S. And by definition, it's a subgroup. Because we're just saying, hey, this is the subgroup generated by S. And you can effectively define that as the smallest subgroup of G that contains all the elements of S. So in other words, if there's some other subgroup of G that contains all the elements of S, then that subgroup is bigger than the cyclic subgroup generated by S. Because this is by definition the smallest such subgroup. Difficult concept. You can effectively think of it as the intersection of all the subgroups that contain S. You could write something like this. You could say, this is the intersection of all the subgroups. I'll call them H. H is a subgroup of G, and S is a subset of H. That's just shorthand notation to say, take the intersection of all the subgroups of G that contain H, or that contain S. S is just a subset. S could be just one element. Then you're talking about a cyclic subgroup. As far as finding it in the examples, it can be tricky. I mean, question is like, how do you find the subgroup generated by the set containing H and V in D4? It's the smallest subgroup of D4 that contains both H and V. And it's a matter kind of trial and error in one sense. This is a subgroup of G. You'd have to check that. And it does contain both H and V, and it's the smallest one. If we got rid of R180, it turns out it wouldn't be a subgroup anymore. If you get rid of, and you don't want to get rid of H or V because they're what's over here. If you got rid of R180, it would no longer be a subgroup. Turns out H composed with V equals R180. So it's got to be in there. And as far as computing it, so to speak, they kind of describe it this way first. In a sense, you're just trying to generate elements of this group by multiplying or composing H and V in various ways to get as many elements as you can. And if you compose them in more ways than you see here, you would still not get beyond these elements. Like if you computed V compose H instead of H compose V, that would also equal R180. If you computed H cubed, it would equal H, which is already in there. V cubed is already V. So this is a bit confusing, like why is that line there? They're just trying to emphasize that, hey, I'm computing things, that's going to give me some new things, hopefully, and this takes checking, but you're not going to get anything more than just what you see here. I'm not going to make a big deal of this notation. It's not something I really focus on. Okay. I do focus on this notation where you just have one element where you're talking about cyclic groups, cyclic subgroups generated by individual elements. We will focus on that. That will be more important for us. I'm going to address the general question here about proof strategies. But first, let me talk about how do you know when to use the one-step subgroup test or the two-step subgroup test. That's a quick answer. Theoretically, in any situation, you could use either test. It's really more of a matter of taste and maybe difficulty level. Typically, when you first are learning the subject, the two-step subgroup test feels easier because you're kind of separating closure under multiplication from taking inverses. The one-step subgroup test people typically find a little trickier because you're combining them in just one step. Closure and inverses in one, in a sense. That's why I think in class I've only done the two-step subgroup test because it just feels a bit easier. But theoretically, you can always use either. There is the finite subgroup test. You can only use when the group is finite, where you can just check closure under multiplication. You don't even need to bother with inverses if the group is finite. It will automatically follow that the inverses, it'll be closed under inverses. Kind of an amazing thing, actually. But that's only when the group is finite. Proof strategies is a tough subject. Certainly as far as like induction goes, it can often be pretty clear that induction might be useful in this given situation when you're trying to prove something is true for all positive integers. That's not a guarantee that induction will be helpful. It's just saying, hey, maybe induction is something to try. And remember, though, if you try induction, and in doing your induction proof, you never use your inductive hypothesis, then you're not really doing an inductive proof. Because the point of an inductive proof is to use the inductive hypothesis, the assumption that you make in the second step after the base case. There are some situations where you can prove something is true for all n without bothering to use induction. There's a really simple example. Prove n squared plus 3n plus 2 equals n plus 1 times n plus 2 for all positive integers n. I mean, it's even true for negative integers, and it's also true for real numbers n as well, but prove that there's no need to use induction because you can just prove it by foiling. You can expand this. Oh, by the distributive property, if you want to be technical about it, I can expand this. Should I be extra technical about it? Let me distribute this through. I'm not going to use FOIL here. I'm going to actually use the distributive property. Distribute n plus 1 through the parentheses here to get n plus 1 times n, and then n plus 1 times 2. And then use the distributive property again to distribute here and distribute here to get n squared plus n plus 2n plus 2. Hey, I really foiled there. To get n squared plus 3n plus 2. Done. No need to use induction. And yeah, this is really true for all numbers n, including any real number, including any complex number for that matter. There's no need to use induction. There's no need to set it up with an inductive hypothesis. I mean, you could maybe do it that way, but there's no need to. So whenever you do induction, it's got to use the inductive hypothesis, and sometimes many proofs, like where you use induction, it's the only way. As far as direct proofs versus indirect proofs, that can be a tough one. Certainly proofs where you're trying to show something is unique. And indirect proof is often better. Proof by contradiction is what I mean by indirect proof. Because if you're trying to show something's unique, like an identity is unique, it's hard to imagine any other argument that you could do than to say, well, pretend it's not unique. What happens? Do I get a contradiction to that assumption? It's hard to imagine any other way to do it. Maybe it's possible, but for most situations, it seems like it'd be very difficult. Sometimes it's a lot less clear. And sometimes you just have to try different things. You have to do some scratch work and attempt it in different ways. I should probably emphasize that a proof by contrapositive often feels like a proof by contradiction, but technically speaking, it's not. An implication, P implies Q, is equivalent to its contrapositive, not Q implies not P. And so you start a proof by contrapositive in the same kind of way you start a proof by contradiction. You start by assuming not Q is true. That something's not unique, for example, that there's at least two elements. In a proof by contradiction, you try to use that to get a contradiction, like 1 equals 2. Contradiction, 1 does not equal 2. Whereas in a proof by contrapositive, you try to prove the opposite of P, the thing you're assuming in the theorem, the premise of the original theorem. So they start the same way, but they don't really end the same way. Proof by contradiction versus proof by contrapositive. I think, want to continue asking you for questions. And considering that as part of your participation, I don't know that I'll have as much time necessarily every class period to address all the questions as I tried to today, because that took us the rest of the class after your example. Because in general, I'd like to do a lot of examples in class, do computations, which again, you can effectively think is analogous to your practice problems, which maybe means you don't need to spend as much time in the practice problems as you would if you weren't in class. In the practice problems, you don't have to do all of them anyway. Just do as many as you feel like you need to really get it, which does still mean allocating enough time, but that's a time management issue that you have to try to wrestle with. I don't know if you noticed, but this is a 4-credit class, so technically speaking, that's why we meet longer, and that does technically mean in the big scheme of things, the homework takes longer. Real analysis we have is a 3-credit course, which maybe it should be 4 credits too. So I don't know what to say about that. I think if we tried to make it 4 credits though, we would run into trouble with math ed majors already having so many credits as part of their major. We might get some pushback on that. So real analysis, when you take that, might be just something you have to live with as a 3-credit course, but maybe being an equivalent amount of work. All right, have a good day.